Okay, so I told you about the definition, I told you about the syntax. This is all quite abstract, are the properties we want a public key encryption to have. But now let's see how to actually construct a public key encryption scheme that actually satisfies these properties. Okay, so we're going to learn about the Gamal crypto system, which is still widely used. And it was invented in 1985. So before most of you were born. Okay, so I'm going to have to tell you how each operation, how each algorithm works, keygen and candec. So for the key generation, what happens is that we're going to generate a large random prime. Okay, so generate randomly, so the dollar sign means random. A large prime, P. So how large? Well, it depends on how powerful we think computers are today. Right now, for example, 2048-bit is a reasonable choice, but in the past we were looking at shorter primes such as 1028, 1024, but then realized those may no longer be secure because computers became so much more powerful. So we increased it to 2048. So we keep doing this. We keep increasing the size of the parameters as computers are becoming more powerful. So you generate a random large P and also generate a G, which is in, let's say 2 to P minus 1. Okay? Then we're going to generate randomly the secret key. So randomly a secret key K. Okay? Again, the key K is going to be, well, I'm going to say this, but honestly, the chance that you can even put 0 and P minus 1, because the chance that those would be chosen, a 0 or a 1 or a P minus 1 will be chosen upon random selection is very, very small, because this P is on the order of 2 to the 2048 bits. Okay. So this is going to be our secret key. Okay, so this is the secret key. Okay? And then the public key is similar to Diffie-Hellman, to the public key in the Diffie-Hellman key exchange. In fact, this crypto system is based on very similar assumptions. The public key is going to be just G to the power of K modulo P. Okay? So you are going to publish the public key, okay, which is G to the K modulo P, and you're going to keep secret key, obviously secret. Okay, so first, why is it that if I publish the public key, someone cannot tell what the secret key is from that? After all, the public key depends on the secret key. Yes? Exactly. If you were to be able to obtain key K, it means that you can solve the discrete logarithm problem, which we saw last time, that it's very hard to, we don't know how to solve it efficiently. Okay, it's a cryptographic assumption that is very difficult to solve. Okay, so that's why by DLP, so due to the DLP assumption, cannot guess K. All right, great. So this was the key generation. Let's look at the encryption. Okay, so encryption takes as input a public key and a message M. Okay. So again, the message has to be in the range 1 and P minus 1, because we're going to compute everything modulo P, and if the message were to be larger, then it would loop around modulo P, and we would lose that extra information. So we're going to pick, again, a random R. Okay, again, we can say in the range 1 and p minus 1. Okay, so we need to choose randomness because the encryption has to be randomized, as we discussed. And then the ciphertext is going to be these two numbers. The ciphertext is going to be g to the power of r modulo p, and then a second number, which is the message multiplied with the public key to the power of the random value we chose, modulo p. Okay? So this is the ciphertext. So let's take a look at it. Here's the message, right? And this ciphertext is supposed to hide the message. So it better be the case that an attacker cannot compute this quantity. Now, the attacker knows the public key, right, it's public, but they don't know R. We have not published R anywhere. R, it's part of the encryption, we used it, and then we use it in the ciphertext, and then we toss it away, we never use it again. But the R does show up here in this quantity. But again, because of the discrete logarithm problem, an attacker looking at this quantity, they cannot tell what R is. Okay, so R remains secret. As a result, this quantity remains secret. As a result, the attacker cannot just obtain the message from this whole value. Any question? Yeah, question. That's a great point. Yes, G and P can be public. Thank you. So we can put them as part of the public key. So yeah, so you can assume that G and P are public. Okay. And they're public because they'll help us with the decryption, which we'll see in a moment. We need them for decryption. And of course, we need them for encryption as well. Okay, so let's see how the decryption works. Actually, can someone tell me how decryption works? The syntax for decryption is that you get the secret key and the ciphertext. So you're going to have the ciphertext, but then you're also going to have the secret key, which is the K. Okay, so this is the public key, and you're going to have the small k and the ciphertext, and you're supposed to get the message back. And let me call this quantity C1, and let me call this quantity C2. And, okay. Can someone tell me how you can decrypt if you know small k? Anyone wants to propose how to decrypt? So again, you know the small key, so you know key k, okay, the key k here in the public key, and you know this ciphertext, and you're supposed to get back the message M. You don't know the randomness R, though. Yeah, exactly. So if you have C1, you can raise C1 to the power of the small key k. And guess what you're going to obtain? You're going to obtain this amount. Okay? So then you take C2 divided by C1 to the power of k and get the message M. So let's write that out. Great. So we have all we need here. So the decryption with the secret key of the ciphertext that consists of C1 and C2 is the following. I'm going to argue that you take C2 and you divide it by C1 to the power of k, everything, of course, modulo p, and I'm going to argue that you're going to get the message back. Okay, so let's check this. So let's write out. C2 is M times public key to the R. So let me write out what the public key is, JK, modulo P, everything to the R, modulo P, divided by C1 is J to the R, modulo P, to the power of K. Okay? And these two quantities are the same, right? It's G to the K times R or G to the R times K. It's commutative in the exponent, so you get the message back. Okay, so this encryption scheme has correctness. Okay, so we just checked the correctness correctness property.